All right, welcome everyone. We have here a little hockey puck here, and its velocity is 0. We can see the position versus time graph here for the x-axis and the position versus time graph here for the y-axis. And it's flat, which means it's constantly whatever that position is, and we have it right at the origin. Each of these grid spaces is a meter, so the cool thing about the simulation is we removed all forces. We're looking down on top of it, like as if it's on a table, just like the demonstrations in class. So what we're going to do is going to do all the demonstrations that we have. This is the puck rests on a level floor and experiences no horizontal forces. What does it do? You're looking at it. All right. Now I'm going to give it a little push to the right to get it started, and you'll see my velocity vector grow. Okay, it's not there yet, but there it is. See my little velocity vector right there. Now I have a velocity. Now, here it is again. It's moving to the right on a level floor. We're looking down on it, and it experiences no additional forces, no extra horizontal forces. What's true about its motion? Take a look at the position versus time graph. If I were to clear it, we should see that we have a straight line indicating constant velocity. And that the y, we're not moving in the vertical direction at all, so there's nothing to see here on the y-axis. All right, let's bring that back to the beginning here, and we are going to look at the next thing. Here it is, resting on the floor, and again, it's at constant position, constant velocity of 0. What will happen when I have a constant push to the right? You will see this constant push as a white arrow that says external. Here we go. 3, 2, 1. Watch what happens to that velocity vector. As soon as I let go, that velocity vector doesn't change. But while I was holding it down, the velocity vector increased, showing that a change in velocity occurs when there is an unbalance of forces. And now we're back at it again with balance of forces, even though it's still moving. So we're back here again. We're going to let it be at constant position. Now, let's say we are moving to the right. All right. So there's our motion to the right. Here we are, motion to the right, nice and constant. And now we're going to push more to the right. What do you think is going to happen? Oh, look at that velocity change. Yes, absolutely. The velocity changes, but as soon as I let go, the velocity is constant again at a higher velocity, but still in the same direction. And we can see that in the graph here, where the change happened, where it was going before, and where the change happened, and where we're afterwards. Awesome. So let's try one more thing. Oh, we got a lot of things to try. All right. So now what I'm going to do is I'm going to mess around with the mass. The cool thing is about this thing is I can actually change the material a little bit. The mass is 0.69351 and 0.7. I'm going to change it to 0.14. Oh, excuse me, 1.4 kilograms. I have essentially doubled the mass. I still am going to apply the same force. I am going to receive the same constant push to the right. All right. I couldn't replicate this in class, so I can do this with simulation. I've doubled the mass. Let's take a look at how it reacts to this. Okay. Here I am going to push. Here we go. Interesting. It's taking longer for me to get it to that velocity than before. All right. I'm going to stop it, and we're going to see how long it takes if I go back to half the mass again. All right, we're at half the mass, and now I'm going to press and wait for that arrow to get longer again. Whoa, it's much more responsive. Geez, it's quicker to get something that has less mass to go. Interesting enough, we figured out something about if there's more mass, the same push will produce a lower amount of change. Cool. And we can see that right here in the curve. This curve takes a long time. This curve goes pretty fast, and we're pretty much going the same speed that I had before. I tried to make that parallel. It's not quite exact. It's actually going a little bit faster, but you can see the amount of time it took here is way, 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 way smaller than the time it took before. So here's my speed at the end. My velocity was 4.88 meters per second, and my velocity here was 4.16. So I was going a little bit faster, but in the amount of time of my change, it happened pretty quickly. The amount of time in my change from zero velocity to that velocity, it changed the time by quite a bit. It was 2:15 to 2:18. All right. So 3 seconds. Here we go again. All right. By the time we get to 4.1, let's see. At the beginning it's 2:30, and now it's 2:30, 41.5. Looking for that 41. I'm way past it. 2:30, and it took only 2 seconds this time, or less, to get it to the 4.1 speed. Yeah. Now, I interchange speed and velocity. We are talking about a straight line motion here. It's always going to the right, so I can talk about just its speed right now. But technically, I am talking about velocity because it is going to the right. So let's go ahead and bring this back to its origin. And we're going to reset these graphs. Now, let's look at number 6. We're on our worksheet that we had in class. The puck is moving to the right while experiencing a constant force to the left. So let me get it moving to the right. Okay, nice and fast. We're going to make that velocity arrow nice and big. I'm going to make it the same size as my force vector or so. They are different vectors, but they represent vectors, these arrows do. And we have a velocity here. This is not a force. I am not pushing on it right now. Now, I'm going to push to the left. What do you expect to happen with the motion of the object? Here's a constant force to the left. 3, 2, 1. What's happening to that velocity? It's slowing down. Slowing down. I'm still holding it. Still holding it. Whoa, it stopped momentarily and it's coming back. Look at that shape. Now I'm going to let go and I'm going the same exact speed, but now in the opposite direction. If I take a look at my graph, when I pause this, check it out. I have a velocity of 6 meters per second, and over here I have a velocity of negative 5.6. I was pretty darn close. I wasn't exactly right. So to the same speed. This one, it's going a little bit slower on the way back. But you can see that as we pushed on it to the left, it slowed it down, causing the position graph to get a curve. And then we let go and it became straight again. It stopped curving. So we can see that all along there. Cool, huh? All right, let's go put it back to where the origin was, and let's go on to the next thing. So we had an unbalanced force to the left, caused the already moving puck to slow down. Now here's the fun part. I'm going to get this moving in the horizontal direction. So I'm going to apply a momentary force to get it going to a nice clip. Here we are. I'm going to get that velocity up to about there. Let me slow it down a little bit by applying a force to the opposite side. There we go. We have constant velocity in the x direction. Yes, and we have constant velocity in the y direction, which means we have constant velocity overall. All right. So notice that all the motion is horizontal. It's only to the right. Now, I am going to give it a little kick. Here we go. Kick upwards. What's going to happen? Watch the graphs. Kick upwards. Whoa, we're speeding up, definitely. But the x graph didn't change. The y graph did. And now we stopped kicking it. It is now going at a constant velocity, a faster constant velocity than before. So thanks for watching. I hope you had fun with this one.